Hi, everyone. We're going to get started. We are Eve and Ellie, and we're software engineers in Google Australia. And we're here today to talk about open source package requirements. So before we get started, here's a bit more about what we do. We're part of the Google open source security team, and which aims to make open source more secure. Sorry. It's made of a number of projects, including OSV, Salsa, and Deps.dev, which is the project we're working on. And Deps.dev collects data about open source package dependency management and aims to help consumers and maintainers better understand and work with their dependencies. So we collect and analyze data about 1 million of open source packages from across several ecosystems and make the data freely available via a website, a BigQuery dataset, and an API. So here are the topics we'll be covering today, and onto the intro. So dependence on open source code is growing. According to Sonatype's last year's report, on average, Maven, NPM, PyPI, and NuGet packages downloads have increased year over year with 52%. But as our open source package consumption grows, the rate at which malicious packages are discovered is also growing, even faster. So in this talk, we'll examine the fundamental tools through which we can analyze and manage packages. Let's take a step back and focus on a single project, your project. And as you contribute to your project, you realize there's an open source package you can use that is exactly what you need. And let's call this package A. You decide to import package A, and it's now a dependency of your software project. And as your project progresses, project A may also evolve. There may be bug fixes or shiny new features. So it's helpful to keep track of all these updates. A standard way to keep track of package updates is versioning. We have widely adopted Semver 2 for package versioning. And typically, versions have major, minor, and a patch parts, those 3 parts. And they could have also other parts like pre-releases and build information. Generally, a major part bump means an incompatible API change. A minor part bump means a functionality that is added in a backward compatible manner, while a patch bump means a backward compatible bug fix. This standard is difficult to enforce, but it's the idea behind Semver, and for most part, we all agree. But of course, you also have beautiful NPM packages like this, or PyPI packages like this. Going back to your project, as new versions of package A are released, we might like to specify the ones we allow. So, for example, we might want to avoid buggy or vulnerable versions of the package, or we may only want to allow the range of versions after which breaking changes are introduced. So to limit versions, we use requirements. Here we have expressed our constraints in words. We are allowing any package with version major part 1. A dependency resolution tool like NPM, PyPI, Cargo, or Maven reads the requirement and selects a version that satisfies that constraint. The reason we typically use a tool to do this is because it quickly gets really complicated. And so in the way our project has a dependency, our dependency might also have dependencies, which can also have requirements of their own that also need to be resolved. And a project doesn't typically have 1 or 2 dependencies. As you can see on this graph, there's a lot more. For example, NPM has more than 100 indirect dependencies, and Cargo over 50. So your dependency graph is less likely to look like this, and much more likely to look like this. Yes. This is Kubernetes at version 1.22.1. So if you're going to have any hope at starting to manage our real dependencies graphs, we need to understand our fundamental tools. And that starts with versioning, requirements, and then dependency resolution. So far, we've written our requirements in words, but we need something machine readable and more precise. We've seen that versions typically look like Semver. This is an ecosystem agnostic way of understanding and writing versions. But what do requirements look like? Suppose we want to express that we allow any version of package that has the major part 1. And we're wondering how to express this. The answer is actually ecosystem agnostic. Ecosystem specific. And here are a few of the ecosystems that we study in Deps.dev. We have NPM, Rust, Maven, RubyGems, and so on. Each of these ecosystems, of course, has their own requirement syntax. So to describe any version with major part 1, we need to know what ecosystem we're in first. So in PyPI and RubyGems, we write it like this, using the comparator operators. So this is greater than or equal to 1 and less than 2. But in Maven and Nugget, you would also have interval notation. And if you're NPM in Cargo, the conventional way to write this is actually using the caret operator. And in Carthage, there's a special operator for these kind of situations, and it's called the optimistic operator, which allows you to lock in as many parts as you can specify. And finally, in Go, there's absolutely no way to describe this. Go only has a way to describe a version greater than or equal to, but you can't put a stop at 2. Sorry, greater than or equal to 1. So similarly, the same syntax across different ecosystems can mean different things. For example, what does this plain version mean as a requirement? It can mean anything from exactly version 1 in case of NPM and RubyGems, or anything at all in the case of Maven. And of course, it is also illegal in systems like Carthage and PyPI. So while there's a de facto standard for version specification, Semver, there is no corresponding standard for specifying requirements. And requirements are built on top of versioning. Unlike requirements, which are highly ecosystem specific, unlike versioning, requirements are highly ecosystem specific, and because of that, it's not surprising that everything that we build on top of requirements is also system specific. And so that's dependency resolution or vulnerability management tools. And so manifests also need to be parsed separately. Requirements need to be dealt with per ecosystem. A system for versioning, a syntax for requirements, and a dependency resolution tool are the fundamental tools for open source packaging. And we need to understand them well to understand what we're doing. So in this talk, we're aiming to propose an ecosystem agnostic way of thinking and reasoning about requirements, because we think that even though there are many different syntaxes, they all strive to represent the same thing. So instead of thinking about requirements in a system-specific way, we could have a shared model and language for thinking and reasoning about requirements. And if requirements aren't system-specific, our tools we build upon requirements also don't need to be system-specific either. So we can have shared ways of tackling dependency resolution, shared ways of dealing with vulnerabilities, and shared update policies. A shared requirement model will reduce duplication of effort. So currently, there's a dependency resolution tool for each ecosystem, and of course, each of them works differently. So later in this talk, we'll actually show how the multi-platform OSV tool has leveraged a shared requirements model to handle vulnerability management. And a shared model can also help ecosystem owners define their own operators much more precisely. Currently, many ecosystems poorly document their requirement syntax and semantic. Many of our code repositories are also multi-language, which means it's much more natural to manage several ecosystems across your dependencies rather than just one. So a shared model will prevent us from reinventing the wheel. So some requirement syntaxes are less expressive than others. For example, many ecosystems don't consider expressing vulnerable ranges when creating their requirement syntaxes. So OSV, for example, needed to invent their own syntax for expressing those vulnerable ranges, and often falls back to listing all vulnerable versions if it's otherwise too difficult. And so finally, a requirement model will give us better language to reason about dependency resolution. Great, so we've made it through the intro. Now that we are all on the same page, let's look at some requirements. It's time for a pop quiz. We've obviously seen some ways that requirements are incompatible. We've also seen some idiosyncrasy between languages. So let's just focus on an ecosystem, just a single one, Maven. Let's do a quick show of hands. Who thinks that 1-1 is less than 1.1? Okay. Who thinks that 1-1 is equal to 1.1? Great. Who thinks that 1-2 is less than 1-1? Okay. Who thinks that 1.2 is less than 1-1? Okay. And who thinks 1.alpha sigma is bigger than 1.b? Okay. So, to anyone who raised their hand, congrats, you're correct. But also, if you didn't keep your hand throughout the whole time, you're wrong. Yes, this is the source for Maven if you're interested and you want to look up all those fun requirements. So obviously, there's a lot more to the set of versions available for a given package than meets the eye. So let's go through them a bit more formally. So let's call the versions available for a given package the version space. The version space starts at 0 and has no end. There is no version before 0, but there is an infinite possibility of versions greater than 0. As a side note, the lowest version, which is the 0 version, is different in ecosystems, which order pre-releases differently. We have also seen that packages can specify versions in various ways. For simplicity, we are explaining the semi-formal mathematical model, and we limit our discussion just to minor, major, and patch versions, part of the version. But the concept obviously is easily extendable to beyond Semver too. So there are arbitrarily many possible versions between 1 and 2, and a strict boundary between major version 1 and major version 2, and 3 and 4, and so on. There are also arbitrarily many versions between minor version 1 and 1.1, and between 1.1 and 1.2. The version set is also constantly changing, with versions being added and deleted over time. So as development of the package continues, new versions of packages may be published, which might be new features, bug fixes, or even in some ecosystems, versions effectively removed entirely. Finally, Semver 2 says that the versions must be ordered, and more specifically, totally ordered. A total ordering means that given any two versions in the space, one version must be equal to, less than, or greater than the other. The ordering is independent of when the version is actually published. In reality, though, ecosystems customize Semver's total order rules. So it's Semver in conjunction with those ecosystems that defines the total ordering. So far, we've assumed that a version space is Semver. But what if it's not actually Semver? For example, Debian and PyPI allow for epoch versions. Nuget allows for more than 3 parts. As we saw earlier, Maven allows for all sorts of things, including for pre-releases to be specified using a dot. Debian allows for revisions. And who knows what happens with various non-ASCII characters, which are allowed in many systems, including Nuget. But the concept of version space still holds. A snowman still fits in the specific, if somewhat arbitrary, spot in this space. And as far as we know, all ecosystems have a total order. And as long as there is a total order in the ecosystems, requirements will work. So to go back to our pop quiz, we can put all versions in order. So 1-1 is equal to 1.1. Sorry, 1.0 is equal to 1.0, which is less than 1.b, which is less than 1-foo, which is equal to 1.foo, which is less than 1.sigma, which is less than 1-1, which is less than 1.1. So back to our simplified version space, a requirement specifies a subspace of this space of versions. We saw earlier how there are many different operators across different ecosystems. Here's a delightfully simple table we constructed showing you just what those operators are. You might notice there are plenty of gaps there. Those gaps can make it hard to tweak specific versions, which may be really handy for avoiding vulnerable versions. And that's why my favorite operator is the not option, which can be really used in that case. And of course, it's only available in RubyGems and PyPI. But ultimately, all these requirements specify the same thing, or like try to specify the same thing. They specify allowable subspaces of the live version. And our purpose here is to define what requirements patterns can do, so that the packaging system can define the meaning of its operators precisely. So we propose that the way we think about requirements can be a lot simpler than this. Really, all of them can just be described using intervals and union between those intervals.
We're going to borrow the interval notation to describe our mathematical model for requirements. We have the square bracket to represent a closed interval and a parenthesis to specify an open interval. We can express single versions as closed intervals containing just that single version, like this interval that specifies version 2. Or we can express multiple versions in a closed range, like this range, which includes versions 2, 2.4, 2.9.1, and 3. We can include or exclude at the boundary by using parentheses instead of square brackets, like in the example here where we exclude 3, or here where we exclude 2. If we wanted any version greater than 2, we can specify that using the infinity symbol. And if we wanted any version less than 2, we can specify that using the 0 version. If we wanted a disjoint range of versions, like any version less than 2 and any version with major part 3, we use the union operator. It might not seem very useful to specify a disjoint range of versions. In Semver, the major part is supposed to specify incompatible API changes. But we'll see as this talk progresses a few ways in which specifying all kinds of unions are useful. There's one last operator we think is really useful, but it doesn't exist in many ecosystems. Suppose we want any version between 2 and 3. The new major part 3 may introduce breaking changes, so we don't want to include 3. We can describe this as 2 to 3, but not including 3 itself. So far, so good. Suppose then some time passes and a vulnerability is reported on version 2.4. Now we want to rewrite this requirement, excluding the version 2.4, but only 2.4. We could write this as the 2 remaining valid versions starting with 2, but this requires knowing the live set of versions in advance, and of course that set might change. Each time a new version is introduced, that means we'll need to rewrite this requirement. And that's where the exclusion operator is useful. To exclude 2.4 from our set before, we can subtract 2.4. And if we wanted to exclude any version starting with 2.4, we could use the infinity operator. Technically, we can just express this with a union, but the subtraction helps to clarify the requirements. And ultimately, our goal is to better understand and reason about our requirements. Now that we have our model, we can translate any of the syntax from any ecosystem that has a total ordering into this model, with the equals operator just becoming the interval of one version. So to summarize, to clearly communicate all of the operators in this table, all we need is range, union, and exclusion. And now that we've finally finished clarifying requirements and how to specify them, let's see them in practice. We just saw how the resolution of requirements against a version space leaves us with sets of versions. But it doesn't yet leave us with a dependency resolution result, where a single version is chosen for each dependency package. In the same way that Semver 2.0 is the foundation for requirements, requirements are the foundation for dependency resolution. As a quick refresher, dependency resolution is the process of taking a set of version requirements and deciding which versions of each dependency should be used in the build to satisfy all those requirements. The usual approach is to read a requirements file and choose a version for each package that satisfies the requirements. This process gets performed by a dependency resolution tool like npm, yarn, pip, or cargo. The tool not only needs to select versions for the direct dependencies, it also needs to select versions for the transitive dependencies. That's the dependencies of your dependencies. This is because dependencies have their own requirements, which may have their own requirements, and so on. The output of the resolution process is called the dependency graph. The interval syntax we've described enables us to speak about dependency resolution in more precise terms. For example, suppose there's this popular package B that's imported both by your project and one of your dependencies, package A. The dependency resolver needs to pick a version of package B that satisfies both of these constraints. We can transform the requirements into the interval syntax we introduced to precisely describe the allowable version space. This might look something like the intersection of these sets. So if you have two different requirements, and say in Maven, we need to find one package version that satisfies both of these requirements. Or maybe it's the union of these sets if we're working in an ecosystem that allows us to have multiple versions of a single package, like npm. It might seem moderately straightforward to keep 3 packages and 2 sets of requirements in your head. But genuine, authentic dependency graphs in the wild often look a lot more like this. You can see why having robust tooling that works with clearly defined requirements is really important. Let's look at OSV Scanner as an example of where this requirement model has been useful. The OSV Scanner is an open source tool based on the open source vulnerability database, which contains information about vulnerable packages and their patches. OSV Scanner does what it says on the tin. It scans for vulnerabilities. It reads the log files of your project and identifies the vulnerable dependencies in it. Once you've run the scanner and found a bunch of vulnerabilities in your dependencies, what then? Well, you can use the guided remediation feature to deal with them. Since the OSV database combines vulnerability and patch information, the scanner can suggest fixes. How? Well, by using intervals. OSV uses Deps.dev's Semver package parser, which uses that interval syntax under the hood. Let's use the syntax in a concrete example during in-place guided remediation. We first represent all dependency requirements as intervals and calculate their intersections. We also represent the vulnerability as an interval. We then get the resulting interval from the requirements intersection excluding the vulnerability interval. And finally, we choose the largest version from the resulting interval. Using standards like Semver is helpful because there's a straightforward way to express ranges, parse requirements, and compare versions. But when actually trying to remediate, interval syntax helps us reason about requirements, including the affected and unaffected ranges. Intervals make it easy to exclude versions, meaning we don't need to parse the requirements or compare versions, which reduces complexity. This comes in handy when there are many requirements, as you might see in some more complex dependency graphs. Let's recap our main takeaways. Being able to use intervals to clearly describe the subspaces in which package versions are chosen is really useful. It helps us as developers understand the dependency graph. But more than that, it lets us build tools that scale. Tools that can work on intractable graphs, like this graph from earlier, which, would you believe? This is meant to play a video. Oh, here it goes. Sorry. The 3 seconds of video is going to be worth it. Maybe. Whoa, look at that graph. Yep, one of the worst graphs that we analyze. But these tools can work on even those giant horrid graphs, and they can be leveraged across ecosystems. Ultimately, interval syntax lets those vulnerability remediation tools clearly describe sets, including and especially sets that have vulnerable versions removed. And critically, the notation is still able to be understood. Because let's be clear here, having mystery tools do mystery things to your dependencies, and therefore to your code base, isn't a great policy for improving your security posture. Now that we can understand and scale that understanding, we can reason about our dependencies, and that lets us make good security choices. In terms of practical suggestions, standards are great. If you're a project maintainer, simplify your requirements and choose a fitting strategy. If you're an ecosystem maintainer, please specify requirements in a clear and standard way, and make sure you have regression tests to catch issues when changing the spec. If you're a tool maintainer, be aware of spec changes over time, and sometimes that there are no regression tests to catch breaking changes, and stick to simpler solutions that can be generalized across ecosystems. This is how you can see more about our work and contact us with your suggestions. Thank you for your attention. Any questions?
So some package managers can also factor in the architecture of the environment that the build is being produced in, and not all versions are available for all architectures. Does that fit into that notation where the architecture is a Boolean of, is this available in my input, rather than a number that fits into a nice range? Would that work in that situation?
I think so, like, because in general, you can put everything, even if you don't have some of the available ranges, like as we were mentioning before, if you have just union of ranges, every time a new version pops up, you have to like modify your ranges. And that's why we said, like, if you exclude some of those ranges in the syntax, it's a helpful tool to use. It's not needed. You can definitely continue modifying your unions of ranges in a similar way, but excluding those ranges probably would be more suitable for that situation.
So I love this idea. I love standard things. However, playing devil's advocate here, and things I've seen throughout the rest of this conference as well too, many standards being proposed. How far does that go until everything becomes, I mean, this is like really far in the future, but everything becomes so standard. What if this just becomes a complete landslide? And I'm talking like everybody's now using the exact same programming language. Like, we're literally like making a specific standard, right, for every single thing. And I love this. But at what point when all the tools adopt the same standards, do they just become the same thing? That kind of confuses me.
That's a very meta question, but in general, I think like it will take quite a while for even this to like be accepted as a standard. So if you want like one language to be the standard, it will take even longer, right? I mean, our goal for now is just for requirements to be standard. So maybe dependency resolution can be standard and so on, right? If we go back to that pyramid that we had. And so currently just one thing is standard. If we make more things standard, yes, I know this is yet another standard we're proposing, but but it does work in practice, yeah.
One more thing along with that as well then too. Regarding a standard for this, is there plans to actually put out a tool that can read all of these different things, and then like I understand it's already being used in the thing that you showed up here, but is that usable standalone as its own thing, just to pump out versions in a machine readable format for like anything like that?
Like, is there a tool that exists that to convert from
Yes,
like all
yeah.
the different things
to what you're showing?
syntax?
Yeah.
Yeah, I think you can kind of do that with this. Look, we definitely want tools like this to be made, and they should be made, and that would be part of like the individual ecosystems could kind of specify the translation from their requirements into this syntax. This library that we have, the Semver library, goes some way towards like trying to do that. I'm not sure if it could be totally used as a standalone tool right now, but yeah, that's definitely something that we hope will end up happening.
Did you have your hand up?
I think I'm going back to the same question you had before, is when you do the closure and the graph resolution of dependencies in most languages, you have parameters that are external to a version that are combined to make that closure. So, for example, the example you were mentioning, some library doesn't exist in a platform, you get with at some point on your graph, that node changes, and everything cascades to different paths. How you relate that with this, how you can make something like PyPI to work with those constraints? Because I see in your tool, in the website, you define something like the resolution closure, and that resolution closure is different depending where you're building it. Many different variations. How you make that work?
Yeah, I think that's absolutely correct, that like there are so many different factors that can affect the resolution graph that you get back. So there is no like kind of one dependency resolution graph. Yeah, I think that in terms of like being able to use the like syntax we're proposing to say like you can only include versions for this specific platform or something, I think we could represent those with the different operators that we have, so that the set of versions would only include, when you were doing those resolutions, it would only include the ones that were available for that particular platform.
And as we were showing in the presentation, this is just like a simplification so that we could at least explain it. I mean, it's already a complex topic. I mean, we showed you a bunch of the fun versions that we have. Like, it's arguable whether you should argue for developers to make their packages more standard versus us handling them more, right? Like, if everyone has more standard ways of writing things, it would obviously be easier for us to specify requirements. But yeah.
So I have a quick question about the infinity syntax that you have. I notice, I want to understand what exactly the semantics are of that, because I saw in one scenario you're using it to actually represent infinity. In another scenario, you're using it as a wildcard, where you're like, here I'm actually using this to be like, this is 2.5.anything, as opposed to 2.5.infinity. What's the reasoning for using that same symbol for those two purposes? And like, is that actually correct in how that was intended?
Sorry, I think we were using the infinity symbol as a...
Yeah, so if you go actually right, that slide right there, you have 2.4.infinity. You're trying to say that to represent, I want to remove everything that starts with 2.4.
Yeah.
In this case, you're using the infinity actually to represent a wildcard, not to represent infinity.
Infinity here is also infinity.infinity.infinity.
Yeah.
Yeah.
Well, but
Placeholder there as well.
But if you wanted to actually represent, if you wanted to use it as infinity in a range notation, you would actually need to say 2.4.0, comma 2.4.infinity to actually outlaw all of the 2.4.
Yeah, I interpret that as the last 2.4.
Yeah.
Sure. This was just an example. It's not that
Okay. I wanted to understand like what were the decisions made there.
So a lot of package managers use X in that exact situation. I've written one of these parsers myself in Ruby that normalizes those things out, and X is often used to mean anything. Also, when you talk about infinity, every package manager registry stores version numbers as strings and has a max limit on those things. So it's not infinity because there's a ceiling to the number of characters you can put in a version number. But yeah, X is often used to within communities.
I've written parsers too who use star in that situation as well.
Yeah, I think that's a fair point. And you can look at kind of how our implementation handles the infinity concept in that like library that we showed. Also, obviously, we want to make this a discussion about what it should be like. So if you have other proposals that you'd prefer to see rather than the infinity notation, open to hearing them, definitely. So thank you.
All the way in the back.
You said you had simplified to present. So I'm seeing the infinity symbol, union. Are there actually ASCII characters in your standard to use? Or do I have to look up some way to input this into my text files?
I don't think we're intending for people to like literally use exactly what we're showing on the slides. If you want to have a look at our implementation of it, visit this library, which will show you like how we actually represent these in like a Cody way. Sorry.
I mean, again, this was just a mathematical notation so that it's easier for us to explain to you the whole concept.
Hi, thanks for kind of walking us through the idea of adopting a standard for for requirements. But it seems like the premise is built on an accepted behavior that isn't a standard today, which is the version specifiers themselves. Before we engage in kind of a cross-ecosystem requirement specifier, wouldn't it be a better idea to attack the version specificity across all ecosystems as a prerequisite? And just to kind of dovetail on the like keeping everything, does everything become the same? Considering how each ecosystem, how you clearly have delineated, has so many different ways to express requirements, those have evolved to support those ecosystems' subtleties and intricacies. Would standardizing these approaches reduce each ecosystem's ability to maintain that flexibility to move forward in the direction their communities desire?
Yeah, so I think that like we've kind of got Semver as hopefully a way to just try and standardize versions. I think like even if you standardized versions across all the packaging ecosystems, obviously you've still got to support those like historical versions which don't conform to Semver or whatever standard gets adopted. I think the kind of cool thing about this syntax is that as long as there is a total ordering in the versions in an ecosystem, you can apply this syntax. So it doesn't require that every single ecosystem kind of becomes this one big thing. You can still have all those different operators that express all those different things in the different ecosystems. And then you can translate them to the interval syntax so that we can build tools that work kind of across every ecosystem. And we can have a standard way of thinking about like dependency resolution, for example, which is incredibly complex and done in all different ways across different ecosystems and can be very hard to understand. We could have like one dependency resolver for everything that could still have all those different ways of expressing requirements in the different ecosystems, but would like perform the same way.
Thanks for your presentation. For people like us who work with a lot of different managers, this is a cool idea. I guess I wonder, have you approached any of these package managers yet, and what feedback have you gotten?
No, we have not, I don't believe. Yeah, but okay. I would be interested to hear their feedback.
So it's really cool. And as a tool developer, we really want someone to handle this for us instead of us parsing everything ourselves, because we have to rewriting the comparison method for every ecosystem. So do you also have the plan to support non-Semver versions, sort of like Debian, Ubuntu, such like Linux distributions?
Yeah, I think we believe that kind of all the different ecosystems could hopefully be handled by this interval syntax. So yeah, ideally we'd love to like onboard as many different ecosystems as we could. Also, if this ends up being like an open source thing, people can feel free to contribute to the libraries and stuff, and that could be a good way for different ecosystems to get involved.
Okay, just one more quick question. I really like the dependency graph. Is that on your website for every ecosystem?
Yes, you can go and look at the dependency graphs on Deps.dev. I won't try and play that video again, but no, don't do it. Yeah, cool. I think we've got a link there.
All right, thanks.
Thank you.
I did want to add that I'm realizing that you actually don't technically need a total ordering across all of your versions in order for this to work, as long as you only, like, you still require a total ordering within any set of versions within a range, but you could also have unions across different version flavors, for example. Like an example was brought up earlier about like you have different versions available for different architectures. You could set architecture flags if you can specify that within your version requirement, as long as within a range you're using the same architecture. You can have then unions across other architectures.
Yeah, absolutely. That's a great point. I think that you could definitely do that. Okay, I think we might be running out of time, but thank you so much, everyone. Thanks for all your great questions, and feel free to come talk to us after.